Hi, and this is an extension to Lesson 8.6 entitled Geometric Sequences. You should have your book open to page 539. I guess the first question is, why are we learning about geometric sequences? You know, a lot of times we get this vocabulary, and you're probably thinking the same thing I did when I was your age. Like, why would I want to know this stuff? What purpose does it have, considering what we've learned in the chapter? Well, geometric sequences, when you look at them and you graph them, they create exponential growth or decay graphs. So that's the reason it's related to the last two lessons that we covered and why this would fit here. Okay, a geometric sequence gives you those kind of graphs. Before we get into a geometric sequence, let's talk about something that we learned earlier in the year. We did an extension earlier in the year on arithmetic sequences. Here would be an example of an arithmetic sequence, and let's just review how we learned or how we figured out it was an arithmetic sequence. The first thing we talked about, let me get that out of the way, first thing we talked about was an arithmetic sequence. You can add or subtract consistently to get to the next term. So can you see a common difference of 6 here? We're adding 6 each time to get from one term to the next. So negative 4 plus 6 is 2, 2 plus 6 is 8, 8 plus 6 is 14, and so on. So now that I've established this as an arithmetic sequence and that I'm always adding 6, I could easily find the next few terms of the sequence by just adding 6. 20 and 6 adds up to 26, 26 and 6 adds up to 32, 32 and 6 adds up to 38, and so on. Now, next thing. If I was asked to find the 500th term of the sequence, it'd be kind of crazy to have to add 6 every time over 500 trials to get to the 500th term, so we learned how to write a rule for it. The 500th term of the sequence would be taking the first term, which was negative 4. You can see I put that here. Since we already have the first term covered, there's 499 more terms I have to know. That's why I have the 500 minus 1. There's 500 terms in the sequence. We already got the first one covered. It was negative 4. There's my 499 more terms. And there's a difference of 6 for every one. That's why I'm multiplying that common difference of 6. When you do this, you would get 2,990. That would be the 500th term of the sequence. I even had a problem like that on our final exam. It was something we covered in first semester. Now, with that review, let's talk about what a geometric sequence would look like then. So how is a geometric sequence different from an arithmetic sequence? An arithmetic sequence is a common difference. We can always get that arithmetic sequence by finding what is constantly being added or subtracted each time. Pretty easy to find an arithmetic sequence. Geometric sequences are easy too. We just have to find what the constant ratio is. Geometric sequences would always have a constant ratio. Ratio is a fraction or a division. Let's look at an example of what a geometric sequence then would look like. Here would be an example of something that's going to be a geometric sequence. 5, 10, 20, 40, 80. Here's why. If I compare the second term of the sequence with the first term of the sequence as a ratio, I get 10 over 5, and 10 over 5 is 2. Now let me compare the third term, which is 20, with the second term, which is 10. If I write those as a ratio, 20 over 10 is 2. If I compare the fourth term of the sequence with the third term, I get 40 over 20. That's 2. Do you notice how each time I am getting a common ratio, and it's 2? Because I get a common ratio, let me underline that. Since I'm getting a common ratio, that means this is a geometric sequence. Okay? Geometric sequences mean that we have a common ratio. Arithmetic sequences have a common addition or subtraction. Geometric sequences have a common ratio. Let's look at a graph of that. Okay, if I want to look at a graph of this, first of all, one thing I should have turned these off ahead of time so I have this in order. Let's look at a graph of the sequence we just had. There was the sequence, 5, 10, 20, 40, 80. If I make a table of that sequence, the position is the x value, the y's are the term. I'm going to have to change my scale up here on the y-axis by tens because there's no way I'm going to fit 80 if I just have a scale of ones. Okay, let me plot these now. So 1, 5 would be 1 right, 5 up. 2, 10 would be 2 right, 10 up. 3, 20, 4, 40, 5, 80. And you can see, let me see if I can freehand this, and that was screwed up. Let me just see if I can freehand a little bit here. Can you see the exponential growth pattern that this is creating? Okay, this geometric sequence is creating an exponential growth pattern. That's why we're teaching geometric sequences right now. It's related to exponential growth and exponential decay. How do we find the rule of a geometric sequence? It's pretty easy to do. Let me write that sequence down again. Here's how we write the rule. From the prior slides, we found the common ratio of this sequence was 2. Okay, so we have to know that first. Common sequence was 2. Geometric sequences always have this form. The nth term of the sequence equals the first term. Maybe I ought to label this. Here is the first term of the sequence. R stands for the common ratio. The exponent is the number of terms minus 1. I'll explain that in a minute. Okay, so let's write the rule for the sequence. The rule would be the nth term would be the first term, which is 5, times the common ratio, which is 2, the power. Can you see the first term here? The first term's already accounted for. That's why we're going to have the number of terms minus 1. That's kind of abstract. It'd be easier to show you, and have this make sense if I give you an actual example, which I'm going to do right now. Let's find the 20th term of the sequence. Now, we don't want to find the 20th term by having to multiply this by 2 and get 160, and then multiply by 2 again and get 320. It's going to take us a while before we get to the 20th term. We can do it with just this little rule. So, the 100th term, the 20th term of the sequence, I have 100 in there for some reason. Let me change that. The 20th term of the sequence would be taking the first term, which is 5, times the common ratio. Now, the reason we have a 19 here, there's 20 terms in the sequence. We already wrote the first term down. Do you see that? There's 19 more to go. Is that making sense? Okay, so there's 20 terms in the sequence. I wrote the first one down here. I got 19 more terms to cover. So that's why it's n minus 1. The first term's already taken care of. I have 19 more. If you put that in your calculator, that's a huge number. It's 2,621,440. That's how we can find the 20th term of the sequence pretty quick without actually having to multiply by 2 each time. I don't know if you remember on the final exam when we had arithmetic sequences, I made you find like the 800th term of an arithmetic sequence. If you don't know the rule, like I have here, it'd take a long time to figure that out. Okay? Same thing here. We don't want to have to find the 100th term of a geometric sequence by doing it by hand one at a time. It's going to take a long time. If we just remember, hey, all we got to do is write the first term down, write the common ratio down, and then the exponent would be how many terms we want minus the first term. It's a quick calculation, okay? This video isn't too long today. That's good. I think I've covered what I need to cover here, and the only thing, if you have any questions, bring those to me in class tomorrow, and we can discuss those at that time, all right?